Hi. So I figured we would do a quick recap of what we did in the last session, where we talked about fluid kinematics, which, if you recall, was the study of fluid parcels, of the manner in which fluid parcels move without being too concerned about the forces that are acting on them. Yeah, characterizing the flow of fluid parcels, and in doing so, we mostly concentrated our attention on how to define a streamline and so on and so forth. But before that, even before that, and this will be very useful for our subsequent work in terms of conservation equations and so on and so forth, we defined two ways of looking at the movement of fluids. One was what's called an Eulerian description, or lab frame description, and the other one was a Lagrangian description, or sitting, which is one in which you are sitting on top of a fluid parcel. Yeah. So the Eulerian description would be the description of a fluid as if you are standing outside of the actual fluid. Say you're watching the fluid flow by in a pipe. The Lagrangian description would be what an observer would observe if he or she were sitting on top of a fluid parcel. And before we went on, we took a little bit of time to define what a fluid parcel is. It's a parcel of fluid that's small enough so that there can be many fluid parcels in a macroscopic volume, but at the same time it's large enough so that there are many individual molecules or elementary constituents, as the case might be, to justify the continuum hypothesis. Okay, so this definition of a fluid parcel is a little ambiguous, but nonetheless very important, right? So we talk in terms of some general function f of t. It could be a scalar function which represents the density, or it could be a vector function which represents the velocity of the fluid in general. In fact, I tend to represent velocity by u, so let's write it that way. So in the two descriptions, the Eulerian and the Lagrangian descriptions are typically related by Galilean frame transformation, which involves the fluid velocity. And we started out by writing in the Lagrangian frame. Suppose you are considering a differential change in this quantity f. How is that related to what a lab frame observer would see? Well, it would be a true change in f as discerned by the lab frame, a true temporal change in f as discerned by the lab frame observer, times, of course, dt, yeah, plus a change in f which is due to the fluid motion. Yeah, and that's what's expressed by this. Yeah, you divide all this, a df dt, a rate of change of f with respect to time as discerned by the Lagrangian observer, a df dt. So you divide everything by dt. So this dt goes away, and this dxi dt is nothing but the velocity. Yeah. Well, there's really no, since I'm writing an I, there's no need to assign a vector sign here. Yeah. So, and this I can be, I is x, y, or z, as the case might be, right? So this is essentially or in vector language, u dot gradient of f. Okay, where in this case f is still a scalar function. And sometimes people write this as df dt, and this is often called the material derivative. And to emphasize, this is the derivative, this is the rate of change of f as felt by a Lagrangian observer. So this line represents this equation represents this, or for that matter this way of looking at it, represents the relation between the Lagrangian rate of change and the Eulerian rate of change. Yeah. So the Eulerian observer can observe can discern a rate of change due to true temporal changes, which is represented by this, but also temporal changes that are a byproduct of the fact that the fluid is flowing. And the fluid is of course flowing only for the lab observer. When you are sitting on top of a parcel of fluid, it is not flowing, right? As in there is no real u for the Lagrangian observer. So that was the other important thing, the Eulerian and the Lagrangian descriptions. That was the other important thing that we introduced. And then we introduced the concept of a streamline. It's intuitively obvious. A streamline is something that say a colorless fluid is flowing past and you inject a little bit of red dye or a blue dye in there. The path traced out by this dye, that is a streamline. And you can define a streamline coordinate, say S, that points along the local direction of u, like this. Okay. So S is like so, and the advantage there is that this this material derivative that we wrote down, and this is the way you relate it to this is greatly simplified when you talk about a streamline coordinate S, is greatly simplified, and it can simply be written as where the like that. Okay, so you don't have to worry about this gradient anymore. You can simply write it this way. The other thing we remarked was if ds is equal to dx, dy, dz. So that's what this ds means, and you have a u which is like so. A streamline can be defined either as or equivalently so both of these are equivalent definitions of a streamline, and I urge you to show this. I urge you to show that these are equivalent definitions of a streamline. Yeah. So this is one problem that you can solve, not terribly difficult. Once you understand that the definition of a streamline is essentially this, the S that points along the local u. We then showed a couple of pretty pictures which made it obvious what a laminar flow is, what a turbulent flow is. A turbulent flow is one in which the streamlines are not nice and regular, instead they're tangled. It's the kind of streamline that you expect from your faucet when you turn it on at high. essentially. When you turn it on low, you expect the water to flow out in a nice laminar manner, and the streamlines are nice and well ordered. And if you turn it on high, you expect that some kind of instability will set in and the streamlines will get all tangled. Yeah. And we also introduced something called a stream function, which is defined as something. The negative is a matter of definition. So the stream function is a scalar function psi, and this is how it's defined. And the advantage of this definition is that the delta psi along a streamline equals 0. Psi is conserved. Okay, so that's the merit of this function psi. Okay, we also define another quantity called the vorticity, which is simply the curl of the velocity. This is called, and for a flow for which if the flow is irrotational and and for irrotational flows, one can write it is possible to define a scalar potential phi such that like so. Again, the minus is a matter of convention. Okay, and there's a nice little, and this is because the curl of, because of vorticity is essentially the curl of u, and the curl of any gradient is always 0. Especially the curl of a gradient of a scalar function is 0 by definition. And there's a nice relation between the phi, the scalar potential, and the psi, which is the stream function, and that is as follows. This is equal to 0. And the advantage is, the advantage in writing it, in introducing functions these ways are that the Cauchy-Riemann conditions. I'm simply saying this. We will see this later. Sorry. This is parallels to the Cauchy-Riemann condition in complex algebra. And this is especially useful in describing two-dimensional flows that do not have that are inviscid and also irrotational. Okay, so this is pretty much all we covered up until now in talking about fluid kinematics, and from now on we will start talking about conservation equations. This is what we will start talking about: conservation equations, mass conservation, momentum conservation, and to some extent energy conservation. We won't concern ourselves too much with energy conservation, but and just to remind you, momentum conservation is nothing but F equals ma. This is just that. That's nothing more. Mass conservation is even more basic. It simply says that mass cannot be created or destroyed. Just to recall, what we've been doing so far is a study of kinematics, which is, in short, it's describing the character of the flow without being too bothered about what's causing the flow, without being too bothered about the forces acting on a fluid element, right? And in doing so, we mainly focused on this thing called a streamline, which intuitively, here's some fluid flowing along a pipe, and you say here's a streamline. Okay, this is something that's intuitively obvious. Here's a sphere embedded in a flow, and the streamlines look like that, like this, like this, like this. In other words, the radius of curvature gets progressively smaller as you move away from the sphere. So this is something that's intuitively obvious, and when you move very far from the sphere, it's as if the sphere wasn't there at all. So this is what one calls a streamline, and the streamline for a turbulent flow is one in which the flow is all tangled and so on and so forth. Yeah. So essentially, you can think of it as a collection of velocity vectors, tiny little velocity vectors like this and like this and like this and like this, and you join them together and you get a streamline, right? So you join the velocity vectors together to get a streamline. So this is something that we defined mathematically, and then we also introduced the concept of a stream function psi, something there's a function that's constant. If I recall correctly, it was well, let me not, I'll leave you to go back through the definitions and not bother with it right now. But essentially, we introduce the concept of a stream function. This is a scalar function, and it's useful mostly for two-dimensional flows for which the flow is confined just to x and y. And so the merit of this function is it's something that's conserved along a streamline. One streamline, one stream function, another streamline, another stream function. It almost labels the streamlines. Yeah. And then we also introduce the concept of vorticity, which is a curl of the velocity vector, the vorticity. That. And this tells you how rotational or irrotational the flow is. And just to demonstrate what that means, if, for instance, you have a viscous flow, right? In other words, here is the bounding surface, and here is a free surface of the fluid, yeah. And this is a viscous fluid, so that this would be the x-axis and that would be the y-axis, and there's a viscous fluid, so that the x-directed velocity at this y would be something like this, for instance. And as you move down in y, it decreases. This is an example of a flow, right? Now, imagine you placed a little paddle wheel in here, a little wheel. Yeah. Now, would this wheel rotate in this flow? I urge you to think about it, and the answer is yes. That's because the velocity here is larger than the velocity here. So this would rotate in this way. Okay. So because this is true, the flow is rotational. Okay. So let me write this again here. And that is because this is true. Okay. In other words, if the flow is rotational, there's a non-zero vorticity. Okay. We will see that these concepts have immense practical value when it comes to describing fluids, especially the flow of inviscid fluids. And we also discuss the fact that if a flow is irrotational, in other words, i.e. equals 0, then it can be assigned a scalar potential. And that's simply because that simply follows from basic vector calculus. Okay, and we also discussed a few interesting relations between the scalar potential and just one interesting relation between the scalar potential and the stream function, and we hinted at the fact that this can be, the theory of complex variables can be brought to bear, but we did not say why, and we will defer it to a little later, and I'll show you why. Now, what I want to do from here on is start the discussion of conservation laws. The first thing we will do is mass conservation. Mass is neither created nor destroyed. Yeah. The second thing we will do is momentum conservation. Okay. So, these are the two major concepts that we will cover going forward, and mass conservation leads to, essentially it leads to what's normally referred to as a continuity equation. Momentum conservation is nothing but F equals ma. That's all momentum conservation is. You're doing a continuity equation, and in particular F equals ma you might be familiar with in the context of point particles or rigid bodies. Here you're really writing down F equals ma for a parcel of fluid. Okay. And the one new thing that will arise because we are doing F equals ma for fluids, F, the forces acting on a parcel of fluid can be F can be due to, for instance, gravity. This is something that you're familiar with from the study of point objects. The new thing is the fact that F can also be due to a pressure gradient. This is new. This is something that you would not have encountered while studying point particles, while doing F equals ma for discrete bodies. This is a consequence of, this arises only while studying continua, in particular fluids, right? And as such, again, as with pretty much everything to do with fluids, it's intuitively obvious, right? You know, for instance, if you have high pressure here and low pressure here, fluid will tend to flow from here to here. What am I saying? High pressure here, low pressure here, and there's these areas are separated by some. In other words, there is a non-zero. In other words, there's a pressure gradient. Okay, the fluid is flowing because there's high pressure here and low pressure here, right? So the pressure gradient is causing the fluid to flow. In other words, there's a force on a fluid element due to the pressure gradient, yeah, that's causing it to flow. Before formally writing down the momentum equation, and there are the two guises of the momentum equation for fluids. One is called, it's essentially, although I'm writing this down as two different things, for inviscid fluids. In other words, fluids for which the viscosity is technically 0, and the other one is the Navier-Stokes equation, where they are both the same. They are both momentum equation, except the Euler, it is simply called the Euler equation when viscosity is not included. It is called the Navier-Stokes equation when viscosity is included. It's just historical. We will get to that. But one of the main things I wanted to bring across here is both of these are simply F equals ma. The major new thing that you will encounter while studying F equals ma for a fluid parcel is that the role that pressure plays. Okay, so pressure gradient manifests itself as a force on a fluid element, and that's something new. That's something you wouldn't have encountered while studying F equals ma as applied to rigid bodies. So we will sort of stop here. When we continue next, we will start with conservation laws, and we will start with mass conservation. We will see how this leads to the continuity equation. So this is basically the first conservation law we will encounter. The other thing I forgot to tell you was that we will, you might wonder, I mean, normally one talks about mass conservation, momentum conservation, and energy conservation, right? So why aren't we talking so much about energy conservation? The answer is yes, we will talk about energy conservation. It just gets a little hairy, but we will talk a little bit about energy conservation as well. It's important. All these three conservation laws are the cornerstones of physics, and so they apply equally well in this situation. So we will talk a little bit about energy conservation, but most of our focus will be on the mass and momentum conservation equations. Thank you.